Let's jump right into this explainer. Today we're popping the hood on the exact technical blueprint of the PrismSQL compiler, specifically looking at version 1.6.5. Now, if you've ever wondered how an AI can reliably generate complex SQL without exposing an entire enterprise database to those dreaded hallucination risks, well, you are definitely in the right place. We're going to trace the exact pipeline, layer by layer, exactly as it runs in production today.
But before we dissect the engine itself, we absolutely have to lock in the foundational concept of this entire system. It's called the schema contract. You see, when a user queries PrismSQL, they aren't interacting directly with the database. Not at all. They're interacting with a JSON file that they uploaded themselves. This file defines the table names, the column types, and the explicitly authorized join paths. That's it. It acts as the absolute sole blueprint for the AI. What this really means is that the compiler does its entire job without ever touching or even seeing a single live row of data inside your warehouse.
So, here is our roadmap for tracking a query chronologically. First, we'll meet the PrismSQL compiler. Second, uploading the schema contract. Third, retrieval, schema, not rows. Fourth, translating intent to SQL. And finally, guardrails and honest limits.
Section 1. Meet the PrismSQL compiler. To really understand what this system is, we have to clear up a massive architectural misconception right out of the gate. There are essentially two pipelines in this package, but only one is the public product. The public hosted compile API simply takes a request and returns a SQL template along with its parameters. Its metadata explicitly guarantees that it executes absolutely zero warehouse access. The rows returned are always empty. Now, contrast that with the CRM executor. That's purely an internal tool used exclusively for Insight IT's owned Postgres databases, never customer warehouses. So the main takeaway? The public API orchestrates compilation, but it mathematically cannot connect to your live data.
Section 2. Uploading the schema contract.
Let's look at index time. What actually happens the moment you upload that schema contract JSON? The system takes your file and parses it into distinct document chunks, but pay attention to what's inside them. You get one document per table and one per join path. They hold structural text, things like table public invoices, column aliases, or join logic like inner public.invoice lines. It's mapping the skeleton of your schema, completely ignoring the actual meat of the data inside your rows. No warehouse rows are ever extracted, and none are ever stored.
So what happens to those chunks? Well, they get encoded using a hashing encoder, which spits out a 768-dimensional vector. Think about that for a second. We're translating the rigid structure of your database into 768-dimensional mathematical coordinates. This sets the stage for incredibly precise query matching later on in RAM, entirely bypassing the need to rewrite or read your stored byte data.
Section 3. Retrieval. Schema, not rows.
Now we move to query time. If I type a question in everyday English, how does PrismSQL safely know which tables to use? Layer 1 retrieval relies on some really rigorous math, and the strictness here is just fascinating. It skips the generic words and goes hunting for exact token hits against your contract's catalog. Then, it checks for typos using strict Levenstein distances. We're talking allowing just a 1-character difference for short words and maybe 2 for longer ones. For dense cosine similarity, it enforces a hard cosine floor of 0.58. And honestly, if a match scores below 0.78, the system demands a typo or a shared prefix to even consider it. It takes all of those mathematical hurdles just to map one English word to a potential table.
Then we hit layer 2, which takes those initial hits and scores the chunks to build what is essentially an impenetrable allow list for the large language model. Here's where it gets really smart. It flat out refuses to add related neighbor tables unless they explicitly share a join path that you declared back in your JSON contract. If two tables are logically close but lack a declared edge, the system flags it as ambiguous, and if that final allow list ends up empty, it doesn't toss it to the LLM to take a wild guess. No way. It immediately throws a semantic undersupported error and stops.
This whole process brilliantly highlights what the system is explicitly designed to prevent. Because it uses intent-gated ranking of schema documents, look at what retrieval does not do. There's no RAG over your actual invoices. None. There's zero cross-customer memory leak. It won't hallucinate foreign keys just because embeddings look similar. And crucially, a cosine similarity hit by itself cannot force a from clause into the final SQL. The system demands absolute certainty.
Section 4. Translating intent to SQL.
With that strictly locked-down schema allow list finally in place, we start translating the user's intent into executable SQL through a multi-stage hygiene pipeline. Step 1 is a heavily restricted call to Gemini to generate an intermediate representation, or IR. The system prompt literally forbids the LLM from writing raw SQL or ON clauses. Step 2, the internal engine repairs any missing join types, relying solely on your uploaded contract. Step 3, it parses that IR. If the LLM tried to sneak in any unknown keys or rogue SQL-shaped fields, the entire query gets rejected immediately.
Next up, the hygiene pipeline gets even tighter. We actively strip out any time ranges or filters the LLM tried to guess on its own, like last 30 days. Why do we do that? Because the internal compiler logic must be the sole, definitive author of date filters and deterministic joins. It enforces a strict from lock, guaranteeing the prompt can't suddenly compile against a random table that wasn't authorized.
Finally, the system executes value binding in a brilliant process known as digit lock custody. Values are extracted straight from the original spans of your English prompt and validated against the entire schema contract. This digit lock parameter custody check is incredible because it ensures numerical parameters strictly match the original text. So if you ask for invoices over $50, the number 50 is never, ever allowed to be swapped out or attested by the word 500 by the LLM. Custody is perfectly maintained from start to finish.
Section 5. Guardrails and honest limits.
As we reach the final phase, it's clear this engine respects its own honest limits. There's this great quote directly from the implementation map. Nested and/or in the IR is refused. Complex English is not compiled by growing the IR. Meaning, if a prompt is just too complex, convoluted, or semantically messy, the system refuses to guess. It won't try to magically expand the intermediate representation to handle terrible inputs. It just drops the request.
Right before printing the final SQL template for whatever dialect you're using, whether that's Postgres, Snowflake, or BigQuery, it hits the static shield. This is the ultimate defensive layer. It guarantees that no destructive commands can physically exit the pipeline. The output absolutely must start with select. No semicolons are allowed, 0 SQL comments are allowed. Insert, update, and delete operations are completely 100% banned, and required parameters cannot be empty. It's an airtight lock.
Seeing PrismSQL's obsessive custody over parameters, its total reliance on explicit join paths, and those unyielding mathematical guardrails really forces us to think about the internal tools we're all building. Are your AI constraints this strict? When you implement AI against your own data, are you just crossing your fingers and relying on the model to behave, or are you enforcing an architectural blueprint that makes hallucination mathematically impossible? It's a seriously fascinating engineering standard to aspire to. Thanks so much for joining me for this explainer, and keep building securely.